I would dive into my favorite topic, spillover and compensation. Why favorite? Because I'm talking about this whole my scientific life, and I think I will still be able to talk about it for the next 15 or 20 years of my life, because this is an issue that never has a single and simple solution, but in the same time, it is relatively straightforward if you understand a couple basics. I think that if you need to have a reference and you need to look into this topic in depth, I would definitely recommend you to look up the compensation section in this guidelines for the use of flow cytometry and cell sorting in immunological studies in European Journal of Immunology, from which I have taken this picture that I will then go through some of the points and explain in detail. What I like is this sentence that says that the fluorescent spillover, which can be overcome by compensation, is probably the single greatest source of frustration for the scientist and the cause of a bad data. I would never be able to say this better. This is exactly how I feel about the spillover and compensation. But in the same time, the good news is we can do something about it, although we cannot achieve 100% perfection because of different reasons that are oftentimes met, but we can solve this problem to a large extent. What we have here is a cell that has two different antibodies with fluorochromes, fluorochrome A and B. And then when we detect these fluorochromes, we want to detect one fluorochrome in one detector, but unfortunately, we will always have a spillover of the fluorescence from one dye to the detector of the second fluorochrome. So it will always be a mixture of signals that we collect, and this spillover is called spillover. So this is the term we use, and we need to understand this is happening. We need to design our panels in a way that overcomes the greatest issues of this kind, which we did for you in the EuroFlow panels. And then we have to calculate compensation to mathematically adjust the data to deconvolute which fluorochrome contributes to the signal in a particular detector. So this is the explanation you can read from the curves and from the different tools online about the fluorescence. So you have the excitation curve. Sorry, I need to point with my pointer. So you have the excitation curve of FITC here. You see that the laser is meeting the excitation curve, in this case, near to the maximum. And then this is the emission curve of FITC. And what you realize is that not only you have a signal in the detector for FITC, but you can also see that there is a signal in the detector that is positioned just next to it, which is a PE detector. So we'll always have part of the signal from FITC detected in the PE detector. This is how detectors look like on the instruments with an octagon. What does it look like when you look at a single stain control? So in the FITC single stain control, you have the signal from FITC, but in the detector for PE, you still have some signal for FITC if it's not compensated. This is how it looks like when you look FITC versus PE. So you always have this diagonal shape, meaning this is uncompensated and there is some spillover. It should always be true that the primary signal, the FITC signal, is stronger in the FITC than in the PE. This is the general rule. The spillover is, however, quantifiable. It is a property of that particular fluorochrome and that particular instrument, so it can be used to calculate compensation. Why it cannot be simply copied and pasted from a different instrument? Because it's specific for the instrument filters. That's why you need to measure the single site control. You cannot copy somebody else's compensation. And also, as Saskia said, not even the fluorochromes detected in the same detector does not necessarily have to have the same curve of excitation and emission. So that's why you have to measure each fluorochrome in particular. If the fluorochrome is stable, it can the calculated compensation can be always reapplied, and you have to have a single stain controls, and you have to have a correct single stain controls for the calculation. Now we can look at a single stain control and see 3 different types of signal. So you see this one, and this one. So can you guess which one is properly compensated? Well, difficult, because here you don't have the right view on the data, so you only look at a logarithmic scale. And if you want to appreciate compensation, you have to look at the B exponential scale on a DIVA or a log linear transformation, which is a generic term. So in that case, you would see this is looks like it's not compensated. This looks probably overcompensated, but you have just to appreciate it, you have to look at the exponential display or log linear. But to be honest, even this you cannot judge properly if it's compensated or not unless you read out the statistics. So if you look at the statistics of the positive population and negative population, the median fluorescence intensity of both should be equal. You see it is not, because the P3 gate contains cells that are below 0, so it's overcompensated. In this case, it is properly compensated because they are very similar, if not equal. And what you also see is that the population P3 is broader than the population of P2. So this is the spillover spread. So this is the spread that Saskia was talking about, and you have to be aware that the spread is something that will always be there. It's not a wrong compensation, it is just the result of the compensation process. So you have to understand it is there, and you have to understand what scale it has, so how big the spread is, so that you understand where is the beginning of your the positivity and where is still the background. So until here it's a background which is different for this population and this population. So compensation will correct the central tendency, and compensation problems will show on a bi-exponential display. Compensation will not correct the spillover spreading, so the spillover spreading will be there even in the case of a correct compensation. And now you also should understand that the brightness of the expression matters. So I frequently get puzzled by this question, why, if I have the same compensation matrix, 2 panels or 2 different samples look different. So one is okay, one is not okay, one is wrong. But why, if the compensation matrix is the same? The reason is here again taken from the guidelines paper. If you look at the primary detector, if you have a relatively low expression, and there is a 1% of error in the compensation matrix, you will see this is a mildly increased signal, and you would probably not even appreciate it. But the bigger the signal is, the more pronounced is the undercompensation issue, as in this case, and also the more pronounced is the spreading issue. So brightness matters. I can show it to you on this relatively busy slide, where you have again 2 markers, and you have a marker X here and marker Y here. If the expression of the marker is X is relatively low or middle, in case of 1% over or 2% undercompensation, you don't even appreciate the problem. You might read out different MFI values, but you would not call it a major problem, not visually, not from the numbers. But if you have the same combination of markers, where now marker Z is much stronger, you see it's nearly a log stronger, the same 1% over or 2% undercompensation results in a grossly overcompensated or grossly undercompensated image. So you totally understand this is undercompensation, this is overcompensation. Still, even if the compensation is correct, the population will be much broader, so there will be this data spread that you have to count with. Again, this is because the two fluorochromes are lying next together and their emission curve overlaps. So that's why the single stain controls used matter. So you should always use single stain controls that are as bright or brighter than your actual marker. And this is how you also select whether you prefer to compensate with beads or cells. So this is what Saskia already showed you. Beads are generally okay, but if the signal on the real cells is much higher, you should use the cells instead of beads. Now, another problem are the tandem dyes that are composed dyes of two fluorochromes. There is a donor and acceptor. These are the donor is excited by the laser light, and then it excites the acceptor, and the acceptor emits the fluorescence. But there is still some leftover fluorescence from the donor that contributes to a spillover, and because this efficiency of this transfer is given by the properties of this compound molecule with different preparation types, so different manufacturers, different batches, or even with degradation of the fluorochrome, the proportion changes, and that's why even the compensation values change. So you can see that these are the two dyes contributing with some spillover. And the problem with the tandem dyes is that you have to watch them much more carefully for the differences between the different lots and different manufacturers, and also the particular composition of fluorochromes. So they are good because they contribute to our flow cytometry experiments with a uniquely long Stokes shift, but they degrade when they are exposed to light and oxidative agents, and that's why their spillover would change when stored for a long periods of time. So you want to be extra cautious with tandem dyes, and they differ reagent to reagent or even lot to lot. Fortunately, there are only 3 rules for compensation controls. That's easy, but you have to understand them, and you have to really understand them deeply. So I definitely invite you time to time to have a coffee break with compensation rules and think about them, and try to always find the root case of your compensation problem in any of the 3 rules. So the first rule is the controls need to be at least as bright or brighter than any sample the compensation will be applied to, because the brightness matters. Background fluorescence should be the same for the positive and negative control in your single stain controls. Compensation controls must match the exact experimental fluorochrome. So this is the FITSI versus BB 515 problem that Saskia mentioned. The EuroFlow compensation SOP lists the different reagents that can be used to generate the generic compensation or the tandem-specific compensation. Of course, we cannot list all the alternative reagents because there are just so many. So it might not be complete for your setting. The controls must match your alternative reagents, and we prefer cells to combeads, but there are some cell types that are difficult to find in the sample, so we need to then use the beads. And then you have to understand that the SOP requires that you understand the compensation principles to make correct choices for your routine. So the SOP cannot be written such that it covers all possible combinations of your experimental needs and combinations of the protocols and alternative dyes and everything. So this is where we still rely on your flow cytometry expertise, and you have to be well-oriented in this topic. And this is all I wanted to say to you, so thank you for your attention.